bulk of the wood itself is dead. Inside, this wood is dead. The only part of a wood when a tree is growing, the only part of a tree that's alive is the outside part of the tree, which is the bark and the layers under it. And below the bark, you have the phloem, which is part of the wood which carries liquids which are made of, which are basically water containing sugars and things which come from the leaves. You see, the wood, dear children, a tree when it grows, exchanges or takes in and throws out chemicals through the top and through the bottom. Through the bottom, it has the roots, which take up water and nutrients from the soil, and those flow up the tree through what is called the xylem, whereas the leaves, where they are green, etc., and they, by the process of photosynthesis, they convert water and carbon dioxide, which are in the atmosphere, very simple substances indeed, and by complex processes, they convert them into sugars and then into larger molecules, such as starches, celluloses, and so forth. But cellulose, specifically, is the main thing in wood, you see. Wood is that thing. And there is a thin layer in between the phloem and the xylem, and that's called the cambium. The cambium is the part where these types of two separate types of transporters of liquid are actually generated and where they grow. And this is all just under the bark. Inside, the bulk of the tree is dead. By the way, the word xylem is actually derived from a Greek word meaning, obviously, wood, and the word phloem is derived from the Greek word meaning bark. So we have these words for various languages. Now, that you see, I just wanted to tell you, I had a very interesting experience this summer, specifically on July the 26th. There was a very, very heavy rainstorm in our back garden, and a plum tree which I had, which was beginning to have lots of plums, unfortunately, split in half. The stem split in half, you see, and and I was very, very disappointed. And I photographed, and I said to myself, is it possible to repair it? Because we're going to lose all our plums this year, etc. So what I did was, I tied the two halves, in the next strip here, I tied the two halves together, and this is the reason I wanted to show you, is because when the two halves, they won't grow together, by the way, they won't grow together, but by tying them together, you're giving it mechanical strength so that the two halves continue to absorb through the phloem and the xylem all the nutrients which they produce within the wood, and they can grow independently even though they're joined together. And what you have oozing out in between, this is the important bit, it's that sap which is coming out. Now, it's from that sap on the maple tree that we can make maple syrup. Now, that sap is it comes from the phloem, and it contains the sugars which have been formed ultimately from the leaves at the top, and that sap, and I have the next slide to show you, and please watch carefully. Oh, that's our plum crop. We had an amazing plum crop, thanks to the fact that I got the trees. But on the right-hand side, can you see that little snail? It's having its lunch. It's eating the sap from the plum tree, you see. And that's a very, very remarkable thing, because you see, that sugary sap is food for others, not only human beings. But I was very, very lucky to be able to capture that image. Now, the next word, please, is pyrolysis, and this I'm going to leave up, because this is, if you're not very clever, children, don't worry if you're not. And if you haven't learned all those lists off by heart, one word, pyrolysis. Pyrolysis is derived from two ancient Greek words, meaning fire and breaking down. So that's one word, please remember. And now I'm going to come on to the final product of the combustion of wood, which is, of course, charcoal, which is left at the end. And Oscar has already shown you how charcoal burns, and charcoal is an almost pure form of the element carbon. It is the soot which is produced when sooty flames burn. And furthermore, this carbon is the source of a remarkable number of uses throughout the history of the human race. And I just wanted to show, thank you very much, and also we can get rid of the aeroplanes, dear sir. That would be much appreciated. And I just wanted to show you a few things about charcoal. Now, charcoal is an impure, we finished with that. Thank you very much for turning up, gentlemen. Charcoal is an impure form of the element carbon. Charcoals, they vary, the proportion of carbon in charcoal can be anything from 90 to 99%. But no matter how long you roast that wood for, pyrolyze it for, you will never make 100% pure charcoal. The thing about charcoal, it has a very, very porous structure, and that gives it a large number of uses. But before I talk about charcoal and different forms of carbon, I wanted to say that there are two allotropes or forms of charcoal, the elements carbon, which are not called charcoal, but which are here. And one of them is here, and that is a piece of graphite, that's a crystalline form here. And I have here one other form, and you see here, these are pure diamonds. It was a source of great challenge for scientists to understand, and I'm going to see if you can I hope you can see, these are real diamonds made out of pure carbon. They are very, very valuable. They're rather small, I'm afraid, but I very much hope you can see them glittering, because it's that property of carbon, of diamonds, which makes them so very, very special. They have a remarkable refractive index that makes them useful as precious stones. Now, do you know what? For many, many years, scientists could not believe that this and this are made of exactly the same atoms, carbon atoms, which are found in charcoal. Now, would you believe that experiments were conducted by scientists initially in Florence in Italy, but even Michael Faraday, when he went on a tour of Europe with Humphrey Davy between 1813 and 1850 in Florence, because they were still doubting, they said, how can this be the same as this, the most precious stone in the universe? And they did it by burning. And if you burn some graphite, and if you burn diamond, a very expensive experiment indeed, then equal masses of graphite and diamond burn to give the same mass of carbon dioxide as the only product. Now, Faraday actually described that burning process, because they showed it to him in Florence, and he described the brilliant crimson flame that diamond made. Now, charcoal, of course, is also useful for drawing, as a drawing thing. So I'm just going to use a piece of charcoal just to draw you my experiment number one. And it has been, this is not art, this is science, and I'm just going to show how we can represent the flask which I did the distillation in, the retort flask like this, you see, and using a piece of charcoal, the teacher, you see, can then illustrate this to the students, and we have a ground glass stopper like this, and then we can put the stopper in like that, and then we have our drops of distillate coming off here, you see, and this is our pyroligneous distillate. My word, it's been a lesson in many new words today, and I very much hope, there it is. And here we have, for instance, the flame, which is roasting it. Here we have the bits of wood and the charcoal like that here, and then we put a nice label on it, like this, retort flask here, and we have a nice arrow pointing to it, et voila, and then we can even colour it in, you see. I do love colours, and then we can just shade in with a little bit of blue to show the blue cone of unburnt gas here, then a little bit of purple there, you see, and then we can shade in the smoke which was coming off, which had a sort of a dark, thank you very much, dear Andres, and then we have a colour, the dark colour here, that was the colour of the thing, and so forth. And you see, I'm very quickly making for you a very simple sketch of an experiment which I have done, but using one of the products of one of the experiments, and that is something, you see, there where we can have our pyroligneous liquid there with the oily droplets of the tarry residue there. Thank you very much. I'm not going to sign it, that would be very silly, but please take it away, dear sir. So there we are, another use of charcoal. Now, of course, do you know what? Charcoal is also available in shops as activated charcoal. You can buy it, the chemist buys it. And activated charcoal, this is used for a tooth whitening powder, you see, and you brush your teeth with it, and it apparently makes them white. But I thought they were white in any case, but it doesn't matter. People buy all sorts of things with the hope of improving themselves. And I just wanted to show you that we have here some activated charcoal is used in water purification, has a huge internal surface area, and it has the remarkable property of being able to adhere to molecules and form loose bonds. Now, as I pour this is activated charcoal, which is heated to a very high temperature to outgas it. I'm pouring my cabbage solution, and hopefully it will come through with no color at all. So this is now using activated charcoal to decolorize cabbage solution. Now, it may take a little while to come through. It may take a little while to come through because it has to absorb itself onto the thing. And my dear Andres, I'm going to ask you to bring on the gunpowder box now. You see, I wanted to show you my personal favorite application of charcoal, which is, of course, to make gunpowder. And I hope you're not too surprised by that. Gunpowder, of course, was discovered, or we know the Chinese were the first people to use gunpowder. And I'm going to show you today a little bit, a very quick experiment. Now, Andres, if you put that's brilliant, on the floor, I'm going to very quickly instruct you. Now, you see, it's coming through absolutely colorless. This is a wonderful demonstration. This is a wonderful demonstration, again, of charcoal in action. It is taken out, and the reason is that all the dyes in the cabbage, in the natural cabbage, and also the smells have been adsorbed. By the way, the chemical word we use is adsorption. That means that the molecules in here, the tiny particles of cabbage and the smell, they have been completely adsorbed onto the carbon by forming loose molecular links. You see, intermolecular forces are strong, and they have remained on the charcoal, which is remarkable indeed. Now, dear Andres, I'm going to start off. No, we start off by showing the three. Please excuse me for turning my back. We have had not very much time, but here we are. The gunpowder was discovered by Chinese over 1,000 years ago. Some people debate. How did they discover it? That is a remarkable story in itself, which I don't want to go into detail. But the honest truth is by intuition. At the end of the day, we humans are terribly intelligent. Doesn't matter when we live or what we did, but we can work out lots of things for ourselves. And intuition is one of the ways in which science has proceeded over the ages. I'm slowly moving this stuff out simply because I want, my dear Andres, would it be possible actually to take this away? I've decided to change my policy on this. Thank you so much indeed. And simply because then we can have more space. Oscar, could you kindly take this bowl away? That would be most kind indeed. Thank you very much. We're creating more space, and I still have plenty to show. Actually, not that many enough. Now, the three ingredients of gunpowder are charcoal, which is in here, which are potassium nitrate or nitre here, and sulfur, which is there. And what I wanted to tell you is that you can use charcoal. How did the Chinese discover it? What is it? Sulfur, I wanted to tell you, is a naturally occurring mineral. It occurs in many parts of the world, especially volcanic regions, but deep underground as well. Huge amounts of sulfur are extracted by mining, by some, we call it the thrash process, but there are other techniques as well. We get it out of the ground. It comes out as a pure element, sulfur, quite remarkable. You cannot break sulfur into simpler substances. It is simply an element. Charcoal, mainly carbon, as I told you, and produced when bonfires burn, as we've just seen earlier today. But potassium nitrate is a clever one. And what happens is it's formed naturally in certain soils. The Chinese would undoubtedly have observed this, the fact that the things. Oh, and here we have, thank you so much. I have especially prepared for you, dear children. This is a collection. These are potassium nitrate crystals. And I have grown them for you in this beaker. They are very beautiful indeed, and you are most welcome to come and look at them. And the honest truth is, in many hot countries, such as in India and in Southeast Asia, these crystals grow naturally out of farmyard soils. And where they grew, and where there were embers of fires burning, those fires burnt much more brightly. And now, what I'm going to show you is what the Chinese learned. They learned some examples of these gunpowder in action. Now, as we go first, I wanted to tell you first of all that the gunpowder mixture, which the Chinese invented, and we're looking at, let's say 1,000 years ago, contains 75% by mass of potassium nitrate, 15% by mass of carbon, charcoal, and 10% by mass of sulfur. And those ratios, which sound like beautifully elegant numbers, were established purely by empirical means. There was no chemistry. You can't write a chemical equation. Today, chemists have not bettered the composition of that the ancient Chinese had learned. And as I repeat, this is pure through sheer intelligence and intuition. Now here, I have a mixture of those three, which is just to show you how it burns. If you do this as an experiment at home or at school, then this is not particularly dangerous. You'll be very disappointed with the outcome, because this is how a mixture of these three powders burns on its own. And I have to warn you, this is not desperately spectacular. It will happen, don't worry, there it goes. Hardly gunpowder going bang. It's not going to make you jump out of your seats, is it? Now, please observe carefully. Can you see these little blotches here? That was very slow burning. These little blotches, that's basically unused potassium nitrate, the bits of black unused charcoal. Simply the mixture isn't good enough to enable a rapid combustion. However, what the Chinese then understood, they then, using the technology of flour mills, etc., they thought, wouldn't it be good if we made them, powder them into a much, much finer powder? And then, when they made a much, much finer powder, they ended up with something like this. Now, this is, by the way, they called it serpentine powder. This is coarse serpentine powder, and this here is milled serpentine powder. This has been ground, this has been milled in a ball mill with lead balls crushing it up, making it into a very, very fine powder indeed, for several hours, for 8 hours. Now watch how this burns. It's quite a bit different. It's faster, and secondly, can you see that there are no residues of yellow? Now, not only that, they then used bread-making technology, in other words, dough, mixing with water, etc., and baking it, but not in the case of this. They took the milled powder, they then added to it small amounts of water and alcohol, and then they put it through a sieve, and they allowed it to dry, and they ended up with something like this. Now, this is what we call corned powder. Now, this burns quite a bit more dramatically still, so please watch carefully, because this will hopefully be quite a bit faster. I'm just going to wait. It takes a little while. Sometimes I may have to be daring and shove. Just look at that. Now, now, please, look at that beautiful swooping that we've got. Wonderful. Now, that you say, can that make something go bang? Oh, yes, it could, because this is definitely gunpowder. And that you see, the result of human ingenuity. That doesn't require a great deal of theory, and we not have it. Now, when the Chinese made this, they said, brilliant, let's now use this for some purposes. Thank you very much. And I'm going to show you very quickly how to make a simple pyrotechnic device using it. My dear Andrea, I just wanted to, Andres, I'm going to very quickly wipe down the bench. So please, excuse me, I'll just quickly wipe it down. We must have dry circumstances. Thank you very much indeed. Thank you very much indeed. This is wonderful. And I'm just going to quickly make for you a Chinese firecracker. Now, we have 2 sheets of A4 paper for this. Now, I need my tape and the scissors. Brilliant. Thank you very much indeed. And the way we do this is we roll up, first of all, we have to make, and you know the Chinese, they always interpreted, or lots of things they interpret in terms of dragons and things, and they call this gunpowder the fire dragon, or so things along the very imaginative. And that in the course of human culture, we people are we like having picturesque ideas or analogies. Take that friend. Now, excuse me, if we cut this off, the Andres. Okay, we cut this off. I will now up right up there, and I will now wrap this tape around. Now, what we're going to do now, we're going to now wrap this up like this, and to make a tube. If you give me the roll, just give me the roll. Let me wrap it up from the roll, because it's easy. Just cut that off there. Just cut that off there. Thank you so much. And the way we do it is this. It gives you and what we're doing, we're strengthening it, you see. We're now making a prison for the fire dragon. That's, sort of way you can look at it in a picturesque manner. And we're making it stronger simply by wrapping this around here. And there we are, like that. And now we trim it off with a pair of scissors. Thank you so much. Take care not to let the tape go there. Thank you so much indeed. Now, what we're doing now, we now have a tube. No one will deny that we have a tube. And now what I'm going to do is to seal the tube off at the end, because we are going to put some gunpowder in, obviously, or some black powder. When we do that, we cut off the end like that, and then we bend the end like this, and then we put more tape on. So now, thank you very much indeed, we wrap more tape around it like this. And basically, the more tape you wrap, the stronger it is, the louder will be the noise when the fire dragon escapes. So we have this. Again, thank you very much, the Andres. Now, what I'm going to do, I'm now going to put in some of my powder. Some of my powder, which I have here. And for this purpose, I've got a small jar, which is probably labelled black powder, and a small spatula, the Andres. A small spatula and a small jar. They're probably labelled black powder fast, or something along those lines. Is that the one? Yes, sorry. I have these. I have smaller containers of beer, children, and we've got a small spatula with a small end on. You may not have it. That's the one. A whole handful every tool of mine. Thank you so much indeed. Now, we put approximately 5 or 6 spatula measures in here. I'll do it carefully so you can all see what I did. 1, 2, 3, 4, 5, 6, and 1 for luck. 7. There we are. Here we are. More than there we are. Yes, so there we are. So here we go. Now then, we're down there. And now what we now do, we use our ramrod here to test to see whether it's all got and to ram it down. So we can now test to see it's down to approximately there. What we now do is we cut the end off here, and then we put a fuse in. We put a fuse in with which we are going to set free our fire dragon inside. Thank you, this in here. And thank you very much, Andres. We now put it like that, so that's now going inside there. And then we bend it over. We bend it over like this to make a solid, to make an absolutely enclosed cage. So if you excuse me, I'm bending it over and now going to put lots of tape on it to give it, to make it very, very strong, to bind it inside like this. So there we are. I'm just binding it up. Now can I have my banger cage, please? My dear boy, thank you very much. Now, at this stage, we are now ready to go, and I wanted to tell you what this is. I'm going to set this on fire. Now, if I were to put it on my hand, you see, like that, you will all agree that wouldn't be a very bright move, okay? Because the reason is, it might make a loud bang, it might rip a hole in my hand. So what we do is, we're going to, it's called a firecracker, I like to call it a fire dragon, it's going to be ready. We put it in a cage. This is what I call a banger cage or a firecracker cage, and it's to protect me, obviously, from the effects of this. And this is steel, so there's no way. Now, there is a shelf in there, which you can see, and there are 2 ends which have got holes in them, and that is to allow any product to come off. Now, do we have some safety goggles? And I'll ask Oscar to do the ignition, and thank you very much indeed, Andres. Oscar, safety, thank you very much indeed. There is no real danger. Andres will be well out of the way. Now, the firing range, we have another pair of safety goggles there, Andres. We have another pair. Let's all wear safety goggles. Now, the firing range is here to there, okay? Because the only way you can escape is from there to there. Oscar, I will ask you to light a fuse, and I will then put the end on, okay? So there's the fuse. If you can light a fuse, I'll put the end on. I'll hold it. This doesn't always work, but you make a little bit of bang, a little bit of a spark, okay? So that's, please, let's have the fuse on. Now we go out, sir. I'm out of range. So there it is. Shortly, hopefully, our fire dragon will be released from his cage with an almighty bang. I'm not sure.